Спасибо большое. Ну, извините, я буду говорить по-английски, да? So yes, what I'd like to talk about in this talk is I'd like to talk about this is I hope it's fairly easy to use the libraries if you know how to code in Python, but what's harder is to understand why they work. So I'll spend some time talking about machine learning, statistical machine learning with intuitions, not with math, even though this is math. And then I'll talk about numerical computation in Python. This is what I want to get across you. And so the setting of this talk is basically artificial intelligence, data science, and machine learning. All these things are related. And they've become quite trendy in the last few years. And Python is used a lot for this. So this has actually drawn a lot of people to Python. And the questions I'd like to ask is, what are the foundations of machine learning, of numerics in Python, and how do these things, combine to do the PyData landscape that we know, including scikitlearn. And I'll start by talking about machine learning. Then I'll give an example of how data can appear as numbers. Then I'll talk about number crunching in Python, because this is really how we built scikitlearn. And then I'll say a few words about scikitlearn, but this is not a tutorial. I'll maybe talk about some things that are going to happen in the next year. So let me start with machine learning. And my definition of machine learning, well, one definition of machine learning is that it's about adjusting models, so statistical models, for prediction. So we're going to adjust them on data. We're going to fit them. And a specific problem is the one of recognizing faces. So suppose you come back from vacations and you have pictures of Andrei, I don't know how to say Bill in Russian, so I'll just say Bill, Charles, and Dave, and you want to learn to label them. And so you have a first labeled version. The two challenges are first that the data is imperfect. And anyhow, I'm not sure what is the definition of a perfect picture of a friend. And the other problem is that you want to transfer this knowledge to images where you don't have this knowledge. And this is the challenge that you're interested in. So the simplest method may be just to store all the known images that are noisy and the names that go with them. So you put this in a database. And then when you get a new noisy image, you're going to find in the database the image that is most similar, say as a residual mean square difference, for instance, to the new image. Okay, so you find the image that is most similar to the new image, and then you assign the label. Okay. Now the first thing that you're going to see is that this is not going to work well with pictures of people, because if people are slightly rotated, it completely changes the grayscale value of people. So the similarity, the naive similarity, won't work well. But we could discuss on how to build similarities, and there's a long history of this. But if you know how to build a similarity, this is a method that somewhat works, and it's a real method that's known as the nearest neighbor method. And now, just to see if you're following, how many errors do I get if I try this on images that I have already seen? 0, exactly, right? I'm not getting any errors on the data that I've already seen. What is this telling us? It's telling us that what is hard is to predict, to conclude on new data, but concluding on seen data is easy. And that is something that is very important. The difference between what we call test data, which is the data that we're going to want to predict upon, and what we call trained data, which is the data that we use for training. Okay? Keep in mind that these two things are different, even though they share some statistical properties, and this is what we want to capture. Okay? So to give a simple example, you're trying to say, predict the age of the captain as a function of the length of his boat. And you have data point there, and you're going to try to fit a model. Okay, so you can fit a line, and if you do this, it's a simple linear regression. Now you can also fit a slightly more complex model. And which one of the two do you prefer? Okay, so each time people say this, I need to turn around and go the left one. This one, so the straight line. But this one fits the data better. It's overfitting. What does that mean? Okay, so basically you're telling me that almost everybody, or maybe everybody is telling me that they prefer the model that fits the data less well. Why is this? Well, it is indeed overfitting. And the idea is that minimizing the error on the test data is not the best strategy, because this data has noise. And when we're minimizing the error, we're learning the noise. We're learning statistical properties of the noise and not of things that will generalize. And it goes back to the fact that test data is different from trained data. That's the important message. So we can fit different kind of models, and we can vary some form of model complexity. So here I'm fitting what's known as smoothing splines. So as I vary smoothing parameters, so the more I smooth, the more the model is smooth, and the less well it fits the data, okay? And so then this is known as regularization. Regularization is preferring simpler models where the definition of simplicity, of regularity, is one that is application dependent, but they're general concepts of simplicity that we could discuss but offline, because they will call for mathematical reasoning on, for instance, entropy of a family of distributions. And conceptually, what we're trying to do here, when we're smoothing, we're reducing the degrees of liberty of our model. We're constraining our model, and when we're doing this, we're balancing the number of parameters that we're trying to learn with the amount of data and with the amount of information in the data. That's the important thing, and this is the core concepts of regularization. Regularization consists in decreasing the quality of fit on the trained data to push the models towards a simpler model and to generalize better, okay? So this is an instance of a very classic problem, a very classic notion in statistics, which is the Biasvariance tradeoff. So suppose you're throwing arrows at a target, and you need to put more energy to throw them at the upper part of the target. And this is hard, so when you put more energy, you're less precise. So when you try to shoot at the top of the target, you're being imprecise. So you're scattering arrows all over. But if you're shooting slightly less strong, you're being more precise. When you're doing this, you're doing a systematic error, right? You have a bias, you're always undershooting. But if your goal is to reduce the mean square error, it is a good thing to take this bias, okay? So bias may be a good thing if it helps reducing the variance, and regularization is bias. How do we measure all this? How do we convince ourselves that this model is better than this model other than by intuition? We can test it. We can test it on left out data, all right? So if I come with new data and I look at how well the model fits on the new data, what's the error on the new data, then I'll choose the model that has the smallest error. So I've fitted the model on the test data, on the trained data, sorry. I've used the trained data to minimize the error of the model, and then I'm using the test data to measure it, okay? That's an important thing. So this is, the reason this is important is that this is a way of controlling for model complexity. If the model is too complex and it has captured noise, this noise will not transfer to new data. So typically the way we do it in machine learning is we have, when we're building our model, we have a finite amount of data. We break this finite amount of data in splits that we may call folds, and then we do what's known as cross-validation, which is that we train the model on part of the data, and we test it on another part, and then we change split, and we do it again and again and again, okay? We keep splitting our data. So that's the core aspect of machine learning practice, because this is how we know that our models work well. All right? So another problem that we have is that if I try to explain to predict the age of the captain as a function of the size of his boat, that might not work extremely well. So I might need to add extra information. And I could add, for instance, the age of his daughter, and that might help. So then I'm trying to predict the age of the captain as a function of the size of the boat and the age of the daughter, and I'm going to find a combination of the two. Okay, so intuitively what we're doing is instead of fitting the data in 2D, we're fitting the data in 3D when we have 2 parameters. And if we add more parameters, because this is slightly limited, right? I could add even more parameters, the number of kids he has or things like this. Then we're just building a space that is bigger and bigger and bigger, okay? That's the intuition. It's a very powerful intuition to have. I understand that it may be hard to have intuitions in spaces of 50 dimension, but believe me, you can train yourself. So the problem that we get is that as the space becomes larger, it becomes empty because we have only a small number of data points compared to the dimensionality. So here, I've shown you that with 2 data points, basically, I can't decide which plane goes through, which is the best plane that goes through, even if I have only 2 features, only the length of the length of the boat and the age of the daughter, okay? And it gets worse. So what I'm telling you is that if I'm adding features that should help me describe, that should help me predict, I have a harder statistical problem. So people think they have more data, but it's harder. And it grows harder exponentially. And this is what's known as the curse of dimensionality. The reason it's exponential is you would have to pave this space regularly if you wanted perfect description of the data. And for this problem, we also need a regularization. It's the exact problem as noise. Dimensionality is like noise. It is preventing us from seeing the signal. So the more parameters we have in our model, the more we need to have either more data or more regularization, okay? And so to give you an example of regularization, suppose I'm trying to learn to predict data that's on this sine wave, okay? I can use a model, which is an approximation model, which is that I'm going to approximate the data as constant, as piecewise constant, okay? So basically, because the data is piecewise constants, this is what's going to be x, and this is y. And I'm saying that if x is between 3 and 3.5, then y equals 2. And then if x is between 3.5 and 3.9, then y equals 2.3. Okay, you get the idea? So by the way, this is known as a tree. And the reason that it is a tree is that it's a decision tree, because you're saying if this, then go in this direction. If this, go in this direction. Okay, so you're going down a decision tree. So just to tell you, all the tree methods are like this. Okay, so what you can see here is it doesn't fit the data very well, because I'm trying to approximate a continuously varying function with constant values. So then what people do is that they use an ensemble of trees. So the idea being that they fit more and more trees, and then they combine them in a certain way. So here, this is a combination of 300 trees or 300 staircases that have been fitted in a certain way. And the trick, and I won't describe the details, but the trick is to fit the trees in a way that averages the noise in a certain way, okay? And this is typically a random forest, even though what I'm showing you here is not a random forest, but a gradient boosted regression tree. But they're the same family of model, okay? So what I want to say here is that your model doesn't have to be correct. We're using a model of piecewise constant, which is quite clearly incorrect here, but it's a convenient model. And the reason why it's convenient is that these trees can be run in an extremely fast way. They're just a collection of if-then statements. So if you code them in low level, they're extremely, extremely fast, okay? So one of the different reasons why these models works extremely well is that we can run them many, many times and then average them, and this gives them a lot of robustness, okay? So if I can do a bit of a summary on the elements of a machine learning method, and I have a tiny bit of math, I hope you won't hate me for this. We're using a forward model, which is that we have a function that describes what we're trying to predict, like the age of the captain, as a function of the data observed. The data may be the size of his boat and the age of his daughter, and parameters that we're trying to adjust. This function could be a linear model, but it could be anything else. All I need it to be is a function in the computing sense, which is a function that I can execute, gets data in, returns a value out. I don't need specific details. Well, in general, I don't need specific details on this function. Okay? So it's a set of rules that go from x to y. I need some form of measure of error to be able, well, usually we use this measure of error to train the model, and we also use this measure of error to test the model. So typically, if you're using random forests or gradient boosted regression trees, you can tune them to minimize the mean squared error or the minimum absolute error. And those are two different measures, and we could discuss what properties they have, but I think this is for further discussion, okay? And then what we need is the notion of regularization. And it can be given by choices in the model. And my tree-based models, they have constant values, okay? That is a regularization. Because they have constant value and because they have a small number of staircases, they don't fit the noise, or they don't fit too much the noise. That's the important thing. Or they can be given by a penalty. A penalty would be basically an explicit bias on the parameters of my model. And an example of a very common and useful penalty is to say that if I'm looking at data in the wild and I'm just trying to do correlations between things I observe, I shouldn't trust my correlations because I will get high correlations in random time series. So what I need to do to get a good model is to do these correlations and then decrease a bit the observed value of the correlation to trust it. And by how much I decrease is a difficult choice, but this is a form of penalty. I'm just giving hand waving, not math here. Okay? So that's all nice and good. But many people, when they hear this, they're like, yeah, sure. How does this relate to my data? I don't have numbers, I have text, I have databases, and as always, you mathematician, you like to do nice drawings in 2D and curves, but this is not my problem. So yes, it's true. There's a bit of a culture gap. We in scientific computing like to work with numbers, and the real world works with different things, like strings. If you've ever worked with scientific computing, we represent everything with arrays. So an array is basically a table of numbers, okay? The real world tends to have databases. And we basically do everything with arrays, for the better or the worse. And I'd like to show you that it is legitimate to consider data processing with arrays. And to take an example, I'm going to look at organizing abstracts of a conference. And I took the EuroPython conference because there weren't enough abstracts for me at this conference. I need big data. Okay? And so the EuroPython, a few years ago, there were 200 talks of very different topics. And then the challenge that we're interested in is, can we find some commonalities across those talks? Can we organize those talks in a way that captures the different topics that are there, okay? And we're going to do this with data science, magic data science. Okay, so the code that I wrote did a bunch of things. It would scrape the website. So that's nice because I can use old Python nice scraping libraries. And then it would do data analytics on this with scikitlearn and plotting with word cloud. Okay, so as I said, crawl, scrape, that's nice. And then we get a set of strings. And I need numbers. So what am I going to do? I'm going to do what's known as vectorizing, which means that I'm going to transform these strings in vectors, in arrays. And the way I can do it is I count the number of times each word appears in a string. Okay? And so then each string is represented as what we call a bag of word, which is that it's the frequency of all the words in the string. Okay? Now, we're looking at a Python conference, so not every word will have the same importance, right? So if I'm trying to tell what this talk talks about, well, the word is not very important, but the word performance is probably very important, even though is much more frequent than performance, okay? And Python may not be that important because it may be common to all the talks. So what we're going to do is that we're going to count in all the documents how often each word occurs, And then we're going to do the ratio between the two, okay? The ratio between the frequency in my specific document and the frequency in all the documents. So this is known as a TF-IDF transform, okay? And so here we get a vector of numbers, of floating point numbers, of real numbers, that capture more or less the information, the semantic information of my talk, okay? And then we do this across many documents, so across many talks. And then I have a matrix that is term by document. So it's how each term is expressed in every document. Now, in practice, it's rather a sparse matrix because many terms are almost never expressed in documents, but that's a detail. So then what we're going to do is that we're going to factorize it. And by factorize it, I mean that we're going to find a small number of combinations of terms that explain well the variation of terms across the documents, okay? So we have a small number of combinations of terms that we call topics. A topic here is a combination of several terms that are loaded differently. And then we have a loading of the topic across the documents, okay? And how to do this, this is basically a matrix factorization, so I'm happy. I can go back to math, I can minimize functions and do things like this. And then the challenge of machine learning is to find good constraints on this matrix factorization to reject the noise and find interesting things. And one good constraint that is often used is to say we don't want any negative values in there. So I don't want topics that are loaded negatively. I don't want to say this is not a talk about performance. I want to say this is a talk about performance, or this is a talk about something else, okay? And so non-negative matrix factorization on a TF-IDF transformation of the data works really well. You can try it at home with scikitlearn, for instance. It will capture some information, hopefully. So what we get are things like this. So the topic number 1 is about Python programming. Then we have a topic number 2, which is basically about data science and machine learning. And a topic number 3, which was about something like testing, I can tell. And we get many topics. So what I'm trying to tell you here is that by using these numerical modeling, so by using this numerical modeling, even on things that is not naturally numerical, I can capture some information. Okay? And this is becoming really important these days because I think the breakthrough in artificial intelligence that we're seeing here currently is partly related to this. If you go back in time and if you look 20, 30 years ago, people were trying to do what's known as symbolic artificial intelligence, and it's not dead, it's still alive. There's still really interesting things. But the recent things that we're seeing are really about writing everything as vectors because it's easier to do mathematical modeling of vectors, okay? So with this, I'd like to talk a little bit about how we do numerical computing in Python. And one of the reasons I'd like to talk about this is that this is a strong reason of why Python became so popular in data science the last few years. And I was doing numerical computing in Python before I started doing data science. And I came to this field with a good knowledge of numerical computing. And I think that's very important if you want to do data science to a very advanced level. So the core of numerical computing in Python is a library called Numpy. And let me show you a bit why people in numerical computing love it. So suppose we want to capture the term frequency versus the inverse document frequency across many documents, okay? So for this, we're going to need to, well, here I multiplied. We're going to need to multiply the two numbers. Okay, suppose I've stored the inverse document frequency in a list that I call IDF, and I've stored the term frequency in another list that I call T. So I need to take every element of those two for every term, and I need to multiply the two. So I can write this in Python with list comprehension. This is a very tight syntax. I love it. And it's going to take, in this example, it took 6 milliseconds. Now, in Numpy, the way I will do it is I'll just write the expression on the arrays. In Numpy, these are no longer lists, they're arrays, so they're tables. And I'm writing the expression. And this is significantly faster, much, much, much faster. And you can see that as I vary the size of the list or of the array, the NumPy keeps being much, much faster. Okay, so why is it faster? Well, let me give a bit more detail of how it works. Another bias that I personally have is that because I'm trained, I find that this syntax is much more readable than this syntax. This is a bit of training, because this is an array computing syntax, which is common to R, MATLAB, many array languages, and this is like a general Python syntax. So once you're trained, you might like this. Okay, so in practice, arrays are nothing more than pointers. So if you do see, so what a NumPy array is, it's a memory address, so a pointer, a data type, and then a shape and a stride. And shape and strides are numbers that tell you how you're going to move across the memory when you're trying to address the different elements of the array. Okay? It tells me that if I want to go from one number to the next one, I need to jump in the memory by a certain stride. And then I can jump, 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 jump. And then if I jumped enough, then I need to loop back. And to loop back, I need to jump by the second stride. And in NumPy, this is multidimensional, so I can have as many shapes and stride as I want. You don't need to know this to use NumPy, but this is the underlying model. Okay, this model is powerful because it can represent any regular data in a structured way. So any regular data, I can represent it in an efficient way. So basically, it's like a higher level abstraction of pointers and data types. In practice, in memory, this is just something that is continuous. Why is this important? Because this matches the memory model of just about every numerical library. So the numerical libraries that have been built for years and years and years in scientific computing can be used without copying the data because we're just giving them the pointer. And this is one reason why we're efficient. So in my opinion, NumPy is really a memory model. Okay, so memory computing is extremely fast because we don't need to do time checking when we do this, but also because it creates a direct sequential memory access, right? So in terms of memory access, we're accessing the memory in a continuous way, and that's extremely efficient for the hardware that does the memory access. And that's extremely important. And the other thing is that it can be computing using vector operations, okay? Now, have you noticed that on the graph I was showing, there was something that was happening at a certain point? This is the time per element as a function of the number of elements in the array. And at some point, it starts going up. Do you know why? Memory, yeah, pretty much cache. I mean, memory, if we had even more data, it would be memory. We would start accessing the disk. So the reason is when our arrays are too big, they no longer fit in cache. When they no longer fit in cache, the CPU needs to move data in and out the cache. Now, the important thing in modern memory computing, thank you, is that the memory is much slower than the CPU. So what you want to avoid is to avoid moving data in and out the cache. So I'll walk you through this. So it gets even worse when I'm trying to do real computation. So here I'm trying to do TF-IDF -1, which is something that is often done. So then it gets really worse. Bang, it starts increasing a huge amount. So why is this? What's going on here is that first, there's an array that's computed that does TF-IDF, and then there's another array that's computed that does TF-IDF -1, okay? And each time we're moving data in and out the cache. So this is extremely inefficient. And so we can improve, so you can see this. I mean, the cost here has been huge because we've just moved data hugely out of the cache. So the challenge is going to be to write the code to minimize this. And one way is to use in-place operation. Here I'm using a -equal. The -equal uses an in-place operation. And because the operation is in place, it knows that the data that comes in is the same as the data that comes out. So it has twice less data to move, okay? So if we're moving twice less data, the cost is twice as small. As simple as that. So if you want to optimize numerical code, you're going to be doing basically in-place operations, okay? So this, this can be seen as a compilation problem, and there's a bunch of modern libraries that try to address it as a compilation problems. Thing like numx or numba or lazy array, and this is related to pagination with SQL queries if you're good at SQL. So what I'm saying is that another kind of abstraction can address this, but it's just not universally deployed currently. All right? So the take-home message is that when you're doing array computing, you can either have tiny arrays and then you're limited by the overhead, or huge arrays and you're falling off the cache and you're limited also. I'm going to skip this in the interest of time. The only thing I want to say is that when you have mixed data types and say you have columns of strings and columns of numbers, then it's extremely useful to use a library that's called pandas, and that is basically a blend between the Numpy model and a database model. So it can do things like queries and equals in a very good way, but it's less good for numerics. So I will strongly push people to use pandas when they have mixed data type and to not use pandas but NumPy when they don't have mixed data type. So often what we do is we start with pandas, we munch the data, at some point we fall to numerical values, and we go to a NumPy. Okay? So really what we're doing is we're converting the data as a number, and then we're just importing scikitlearn, and it's easy. And I don't want to go in the details of scikitlearn, but because I'm a core developer of scikitlearn, let me tell you a few things about scikitlearn. So what scikitlearn is a Python library for machine learning. And our goal is to make machine learning easy, but you still have to provide the data mostly as numbers, mostly. The model of scikitlearn is very easy. It's a model of gray box. The idea is that you have building bricks that you combine together, and each building brick is a model, a machine learning model, a statistical model, and they're mostly interchangeable. So the idea being that if I have my trained data as X and Y, so my features and what I'm trying to predict, I can instantiate a model that's called an SVC. You don't even have to know what it is. I fit it on the data, and then I predict, and that's pretty much all there is to know in terms of computing, almost. Okay? And just to give a maybe because I thought some people knew scikitlearn, I just wanted to give you a vision of what's coming up. And so things that are exciting that are coming up is that we're working hard on improving the data input, and we're soon going to have what we call a columns transformer that is able to take a panda data frame in, so a representation of data with different types of data, and to apply different transformers to the different types of data and recombine it back. So if you have strings and age and revenue, you might want to do different transformations, and this is actually very important in data science. So we're working hard to make it much easier, and we're also asking ourselves, how do we handle missing data? How do we handle unknown categories in these things? So if people are on a day-to-day fighting with these things, well, we're working on making it better. And another place where we're working on improving things is what's known as scaling out. So the idea being that we want to use more and more computers. So to be able to use scikitlearn in a distributed way on the cloud, for instance. And I guess the most exciting improvement here is that we're using a distributed computing backend. It's a very simple one that's known as JobLib. So it's a very simple and a very universal one. It is meant to be simple. It is not meant to be complex. But these days, we're able to plug it into powerful backends. Yarn, for instance, if you have a Yarn cluster. But the thing I'm most excited about is that we're able to plug it into Dask, which is a powerful distributed computing model in Python. And we're currently working together with the Dask developers to make this connection really good and basically to get scikitlearn to work well on a distributed computing environment. So I need to finish. My conclusions are that data science and AI are statistics. So they work on numbers, and they worry about capturing the properties of the data while rejecting noise. NumPy and arrays are great for that. And the Python language is perfect to manipulate this. And the reason it's perfect is because it allows us to do low-level constructions with high-level wordings. And scikitlearn is what does the junction. Before I finish, if you want to work on scikitlearn and be paid, come and talk to me.
Thank you very much. Questions? Who has questions? Okay.
Thank you for your presentation. So I have two questions. First of all, do you believe that quantum computers in some near future they will be as real computers and we can use it? So the second question is how they will change all the stuff that you were talking about. Thank you.
So that's a very interesting and challenging question. I do happen to have a PhD in quantum physics, so I'm actually not completely unqualified to answer this, but it's hard to follow what's going on in quantum computing. So the thing about quantum computing, so there are two kinds of quantum computing. There is the very promising one, the one that everybody's trying to get, and there is a simpler one which is known as quantum adiabatic computing. So let me first explain quantum adiabatic computing. Quantum adiabatic computing is about engineering quantum systems that are many body problems, so many different particles in interaction, and finding the equilibrium point of this. So it works to solve a very specific set of problems. And it's basically many-body physics. So, and now general quantum computing is the idea that you're going to replace bits. Well, you're going to use bits, but with quantum physics, what you have is that an atom can be in a superposition of multiple states, okay? And so the idea is that you're going to do operation on bits, but each time you do an operation, you project, well, you divide the atom in two, you divide the system in two superposition of these states. So then the idea is that you can do parallel computing in an exponentially powerful way, because each time you're forking along a computing path and you're doubling the computation. Now, if this were to work, and there are challenges, I mean, it's extremely hard to work on many bits. I don't know what the state of the art is, but it must be around 20 bits. But still, 2 to the power 20 is still quite expressive. Now, the problem with quantum computing is that it's probabilistic. It's because it's basically the whole quantum theory is probabilistic, quantum physics is probabilistic. So it's very useful to find things where you can very easily check the solution. And one good example is factorizing numbers. If I give you the solution to factorizing number, it's trivial to reconstruct it. Now, to answer your question, if quantum computing were to work, it would probably be a game changer for a bunch of things, not everything, right? There's a bunch. It would typically be a game changer for searches and database and things like this. The forefront of AI is not focusing on this right now. I can't really say when quantum computing will be working. Back 10 years ago when I was doing it, we said, in 50 years. These days, some people are claiming that it's closer, but people in quantum computing research are worried about those statements because they seem like advertising, and it seems like they haven't shown anything really hard with quantum computing. So the people who are claiming that they can do quantum computing can do the simple things of quantum computing, like adiabatic computing, but not the hard thing like infinite parallel computing.
Okay. Questions? More?
Thank you for your presentation. In your opinion, what's the most challenging part in machine learning?
Well, that's a very wide question. I don't know. I think this answer will vary hugely between who you ask. I can tell you is that if you do a survey, because people have done this, what people in practice are struggling most with, it's about going from the raw data to a model like the ones we have. So basically, scikitlearn does the easy thing. So people call these things like dirty data problems. I have a research project that I've just started on dirty data, so if you want to work on this, come and talk to me.
Okay, thank you.
Okay, I think that's it.
Thank
Merci
you.
beaucoup. Tu es magnifique.
Спасибо вам.